All right, so can you see the screen, everyone?
Yes, sir.
Okay, great. So is there any question from the previous lecture? No question from the last lecture?
No, sir.
No, sir.
All right, okay, good. So we were doing we started kinetic theory of gases from the topic of matter and section of matter and ideal gases, and we talked about Brownian motion. So let's move on to the next idea, which is how do we model a gas? So let's define the topic as a model of a gas. So, all right. Now we know that a gas is made up of molecules, right? So you can have oxygen molecules, you can have hydrogen molecules, and combining all of those molecules, a lot of those molecules will give you a gas, right? Now these molecules, let me draw them with, I'll just draw them as a sphere, right? And there are multiple molecules, and these molecules are moving because of the Brownian motion that we discussed last time. They'll be moving in a random zigzag pattern, right? So their movements will be entirely random, right? So random movements. So I think I'll write these things over here. So we have a gas which is made up of molecules which are moving randomly. So random movement of molecules. Now let's talk about the structure of these molecules. We'll imagine these molecules to be small spheres. So these are spherical in nature, and they are, we'll consider them as unbreakable. So you cannot break them into more of their into their parts, I think I should say. All right, so these molecules, there is some spacing between all of these molecules, and unless and until they collide with each other, they are not going to interact. So these molecules, will consider them as non-interacting molecules unless collisions between these particles happen. Collision happens. So I'm sure that you're all aware of what do I mean by collision, right? Everyone understands the idea of colliding molecules. So they're just going to collide with each other. They're going to hit each other. And so that's when the interaction is going to happen. All right. So suppose that I put these molecules in a box. So let's draw it over here. Okay, so here's the box. Now let's just draw some random molecules. Suppose I'm putting these molecules in this box. What do you think would happen if I suddenly contain these molecules in a box? In terms of their random movements, they're moving randomly, right? So they'll be moving randomly. They might strike with each other, and one of the things that they can do is hit the walls of these containers, right? So they're going to hit or collide with the walls of these containers. So molecules will hit the walls, right? And when they do, what's going to happen? This will build up some pressure on the walls, right? This will build up pressure. So, and it's pretty straightforward to imagine this situation as well, right? So you have you have some molecules, and you contain them in some container. of course, because of their random movements, they're going to want to, move here and there, everywhere. And that's the reason that they will also be hitting these walls of these containers, and they'll hit all these walls of a container. So this is just a two-dimensional thing. So that's why we have 4 walls. And so it's a square or a rectangle. So we have 4 walls, and these molecules will hit all of these walls when they are colliding. So given long enough time, all of these molecules will hit all of these walls of the container. And because of that striking, there will be some pressure that is going to be built up inside the container. So is that clear?
Yes, sir.
Right. Okay, good. So when these molecules are colliding with each other, because of this collision, what can happen in terms of momentum? Anyone? Momentum will change, right? There will be some change in momentum. Because of course, when they collide, there'll be their velocities will change. And we know that momentum, which is normally written as vector P, is m times vector V. And because when they collide with each other or the walls of the container, the velocity is going to change. So the velocity is changing because of the collisions. So this change in velocity is going to produce a change in momentum, which will be mv. Let's just take m as a factor common outside, v2 minus v1. So first, some initial velocity minus or the final velocity minus the initial velocity. So that's just the change in momentum. Now we know whenever momentum changes with time, that produces a force, right? Because we know that force is really change in momentum per unit time. And this is really how force is actually defined, by the way. And from this, we write it in terms of MA. I'll just show you that for the sake of fun of it, because we know that dP over dt, so P is m times V, but m is a constant, so that will be outside the derivative. And so we'll have dV over dt. And then we know that dV over dt is just acceleration, right? Change in velocity divided by change in time. So that's MA. So that's how you get MA. Just I'm sure that you're already
Sir?
aware of that. Yeah.
Sir, why don't we write delta instead of D?
Oh, it is actually delta, right? So it's actually dP over dt, but we want this force at some particular instant. So what that means is I want an instantaneous force. So at this particular time or at this particular point, what is the force exactly at this time? So what do? We use the idea of derivatives that Leibniz gave us. Really, it was Leibniz, but Newton gets credit for it as well. So when you apply some limit just means that you're saying that delta t is approaching to 0, which means that we are making the time interval so small, it's not 0, but it's going towards 0. So we're making it so small that no, it's not 0, but it is so close to 0. It is extremely small. When you do that, so you can think now that really implies that I'm trying to find out the quantity at that exact interval of time, because this interval is so small. So we get the velocity or we get the momentum or the force, whatever, at that exact interval. So we apply this thing and we say that this thing is delta P by delta T. And this thing is this thing converts to derivatives, which is dP over dt, because the derivatives is defined as something like this: delta anything, it could be delta t and it goes to 0, and some function of t, so it's function of t plus some delta t minus function of delta t, something I don't really remember. I think it's more or less like this, and divided by delta t. So this is dp is behaving as this function, and dt is this delta t, and then this thing goes to 0. So this thing converts to derivative df. You can say it as df over dt. So this is how a derivative is really defined in mathematics. This is function of t, sorry.
Sir, do we have to do anything with functions in physics as well?
Oh, you mean explicitly? No, but I mean everything is a function, right? Force is a function, momentum is a function of time, for example. Displacement is also a function. All of these quantities are really just a function of some variable. But explicitly, you're not talking in terms of these functions like this. So I was just telling you, I was just answering your question that why don't we write delta p by delta t? You could have written that as well. It's just a matter of if you're trying to get it at some instantaneous point in time, or just a general expression for it. So does that answer your question?
Yes, sir.
Okay, perfect. So you'll not be using any of these limits and all these things in physics, at least that's what I'm sure of. So I'll just color not the part of your. All right, anyways, so where was I, right? Okay, so we're talking about this thing, change in momentum, right? So when these molecules are going to collide with the container and with each other, they're going to cause some, there is going to be some force, right? And because of this, there will be also some pressure, right? So it's all of these forces when these molecules collide with each other and they change momentum, and that changing momentum produces force. Then this force is what gives rise to the pressure which is exerted on the walls. Why do I say so? Because we know that pressure is just defined as when force is applied per unit area. So for example, I have an area. This is the entire area of a surface, and I apply a force to this surface, then I am applying pressure, right? So applying force to this area, then that means that I'm producing a pressure on this surface at this point. So that's how the pressure is produced. It is a result of changing momentum, which causes force. And there are so many of these particles which will produce so many change in velocities, and so many collisions will happen. So there will be so many forces, and the sum of all of those forces will produce a resultant pressure on the walls of the container. All right, so is that clear for everyone?
Yes, sir.
Really, the question is, do you understand how is this pressure being produced on the walls of the container physically?
Yes.
All right,
Yes.
perfect. Okay, good. So then now let's talk about this pressure, right? And how would the speed of the molecules relate to the pressure which is produced? So relation or relating between speed of molecules to the pressure exerted on the wall. So I'm just going to write to the pressure, right? It is understood that this pressure is exerted on the walls. Okay, good. So to start this topic, we'll need to make some assumptions, and these assumptions are going to lead towards the case of ideal gas. And so the equation that we are going to, or the relationship that we'll derive, is more only valid for ideal gases. So that's what we'll be doing at this point. All right, so the first assumption that we are going to make is that the forces between the molecules are very small. So that is just that there are negligible forces between the molecules. Now, these are not the forces which are coming from collision. These are the forces that are just existing between the molecules, the attractive forces, you can say. We are considering them to be negligible, not the collision ones. So because of collision, we saw that there will be some forces, and those will be the cause of pressure. But we're not saying that they are zero. We are saying that the forces between the molecules themselves are zero, or at least they're almost zero. The next assumption would be that the volumes of these molecules is so small compared to the volume of the gas. So how do I write it? I'll say volume V of molecules is very, very small compared to the volume of the container or the box, right? So we'll say that these assumptions are pretty reasonable, by the way. Second assumption is also very reasonable because obviously the molecules are so small, and containing them in a container or a box, we know that the box will be a very large volume box. So we can say that, we can make this assumption. It's sensible to do so. All right, so the third assumption would be that all of these collisions are completely elastic. So I'll just say that let's just say collisions are entirely elastic in nature. And the fourth assumption would be that, okay, so you can think of this in terms of when you have these molecules, they're going to collide, right? Now, when these molecules will collide, we'll assume that the time which is spent when they were interacting with each other is very small compared to the time between two successive collisions. So for what I mean is, think of think of two balls, right? And they're colliding. Now, when they'll collide, they'll hit each other. And the time spent during that process while they are touching each other is very small compared to the time when these molecules hit another molecule, and that is the next collision which happens. So does that make sense? It's kind of difficult to get across, but I hope, does that make sense?
Sir, can you
Yes, it
explain it one more time?
Okay, so what I'm saying is when these two molecules, they come together, they're going to hit each other. And when they hit each other, they're going to kind of, you can say, for a brief moment of time, they'll kind of stick to each other, or, they'll be interacting with each other. They're touching each other. Now, the time spent during that touching is so small compared to the time when these molecules get apart from each other and strike another molecule. So there is some time that will happen during this successive collision, and there is some time spent during colliding, which is TC. So when they're touching each other, the time will say it's so small compared to the time that it takes for another collision to happen, right? So they'll hit each other, immediately rebound or bounce back and hit another atom or hit another molecule. So that is what I'm saying, that the time spent during the collision is tiny compared to the time spent, or not the time spent, compared to the time between collisions. All right, so does that make sense now? Is that clear?
Yes, sir.
Okay, good. So, and the final assumption, there are so many assumptions and I understand, but this is the last one. And we say that these molecules are identical. and they are going to move at random, but we have already established that, right? So they are identical and they move randomly. Identical is also sensible. So if we're talking about a gas, we're just talking about a particular gas. So it could be oxygen gas contained in the container, right? So it could be oxygen gas, it could be hydrogen gas or nitrogen or whatever, right? So it could be any of these gases, but it's just one type of this gas. So we can assume that the molecules of these gases are identical. So we're just, the statement is really saying that we have only one type of gas. One type of gas, either oxygen or hydrogen, right? So it's just one of these types. All right, so does that make sense? It's clear?
Sir, only oxygen and hydrogen?
No, there can be more. What I'm saying is that, of course, there are so many gases, right? We have helium, we have argon, we have so many gases. I'm just saying that it would be only one type of gas that we're talking about, either oxygen or hydrogen or helium or argon or any other type. This is etc. But the main point is it's just one type of gas, which is why we can assume that the molecules are identical. So that's clear? Okay, good.
Yes, sir.
All right. Okay, good. So, all right. So now our goal is to derive this relationship. Okay, so just give me a second and let me check what time is it. All right. Okay, so we'll do this. We'll start by considering a cubical box, right? So let's say that we have a box and this box is a cube. So I'm going to try to draw it. Let's see what happens. All right, so I have to ignore the drawing, but you get the point. All right, so it has, a cube has in total how many faces? 6 faces, right? So top, bottom, this one, the opposite one, and the front and the back one, right? So top, bottom, 2, left, right, 3, 4, front, back, 5, 6, right? So there are 6 faces of this cube, and we'll consider a gas of, so I'll just draw one molecule, but we'll assume that there are so many molecules, right? I'm not going to draw all of them, just to make our this so that it's easier for us to derive this relationship. So we'll consider that there's this gas and it has a mass m, all right, and the length of the box, we'll just call it L. Now it's a cube, so this L is all the sides are of the same length because it's a cube. Mathematics, right? Geometry. So we'll assume that this particle is moving at a speed, and we'll call that speed c. Does not mean it's the speed of light, just for the sake of, or you can call it v, it doesn't matter, right? Even if you want to call it v, you can just say that it's moving with some speed v. Now, this molecule is moving in this direction. Now, what would happen if this molecule hits this wall? If the molecule hits this wall, it's going to hit it and then rebound backwards. And that hitting is going to produce a change in momentum. And that change in momentum would be what? It would be P2 minus P1, obviously, which would be M V2 minus M V1. Now, let's see what would V2 be. Suppose that the speed is, because we are saying, we assume that the collision is perfectly elastic. So V2 and V1 magnitudes are exactly the same. But that's where the trick is. Their magnitudes are same, but the directions are not, because when it rebounds, it's going to come back with a negative velocity, right? So I'll have to define a system where I say that right direction is positive and left direction is negative, right? So the change in momentum will be m into minus v2, right? Because, or we'll just now call it v, right? Because the velocities are same, v1 and v2 are same. So I'll just say that there's some v. But it would be minus v because it's coming backwards, right? So it's going to the left now after rebounding. And then we have minus because of this difference in these two values of momentum, and then m, and then plus v. This gives you change in momentum as do the math, and this becomes minus 2mv. So is this clear for everyone, the change in momentum part?
Yes, sir.
Sir, can you explain
Alright,
again?
Okay, of course I can. So we have a mass, right? It moves in the container. We're going to suppose that it's moving initially to the right direction. When it's moving to the right, at one point in time, it's going to hit this wall, which I highlighted as kind of yellow color, and then it's going to rebound backwards. So when it hits the wall, it's going to move with velocity v. It's moving with velocity v while when it's hitting the wall. And as soon as it hits and it comes back, then the velocity would be negative v, right? Because it's now moving in the opposite direction, and velocity being a vector, it would be negative v. Negative sign is just implying to the left, the direction of the velocity. And so I just substituted these values in this expression, m v2, but v2 is minus v because v2 is the velocity after rebounding, and minus m v1. So v1 is just positive v because it's moving to the right. And so just doing the math now, this becomes minus mv, which becomes minus 2mv. And that's the change in momentum. The velocities, both of them, v1 and v2, are same because of our assumption number 3, right? Because we said that they're entirely or perfectly elastic in nature. So the velocities are the same. All right, so is that clear now?
Sir, what about momentum? Like P2 minus P1,
Yeah.
that will also be the same. I mean,
Uh,
how do you consider both of them as only momentum in the next step? Like we are differentiating P2 minus P1, so that's the difference in momentum in the second step.
Oh, right. Yes, exactly. So I'll just write this over here again. So P2 minus P1, I'll write P2 and P1 separately. So P2 is the momentum after it rebounds. So it would be mass of the particle times the velocity, but because it's rebounding, it's moving to the left. So the velocity will have a negative sign. That's P2. And P1 is the initial momentum because of the initial velocity, which was m is the mass, right, times velocity in the right direction, which is plus v. So this is P2 and P1. Now difference in momentum is P2 minus P1. I'll just substitute the values for P2, which is minus mv now, right? So it's minus mv. And then this is P2, and then we have this minus sign, and then P1 is mv. So that's how we got it, right? Now this is just minus mv. So this is minus 2mv, right? Minus 2mv. And that's the change in momentum, delta P, which is P2 minus P1, right? So is that clear now?
Yes, sir.
Okay, perfect. Good. All right, so that's the change in momentum. So we have established that the change in momentum is minus 2mv. Now let's talk about the distance that the object will, by object, I mean this molecule, right? This molecule or particle will travel. Let's talk about its distance. So we know that when it hits the wall, suppose it starts its journey from one edge, right? And it hits this wall. it will travel a distance of L. Then it will move back, rebound, and then when it comes back to hit this wall, it would have traveled a distance total of 2 times L, right? Because it hit this wall. Let me try to do it in this way. So this is the molecule, right? So it comes here, hits this wall, travels it, so it has traveled a distance of L. Now it moves back like this, like this, like this, like this, and then when it is going to again hit the wall, it would have traveled another distance of L, which means that in total the molecule is traveling a distance of 2L, right? So the distance traveled by this molecule before it collides again, before collision happens again, the distance is 2L, right? So is that clear? I'll write it on this side. It's equal to 2L. So if the distance is 2L, then the time taken for this collision to happen would be, it would be distance divided by the speed, right? And we already know, we have established that the distance is 2L, and we already know the speed was v, right? If v is the speed with which it's moving. So the time for this collision to happen is 2L by the speed of the particle, time elapsed between the collision. Having this momentum and this time, I can now write an expression for the force, right? So that was my goal. So once I write an expression for force, then I can easily write down an expression for pressure. And remember, that was our goal. We wanted to find the relation of speed of molecules to the pressure. So having an equation of pressure in terms of this speed v, I'll have this relationship. So it's very simple now. All you have to do is to write down the force, change in momentum divided by the time elapsed, and that is simply minus 2 mv divided by 2L by v. Right? So what does this become? This becomes m. So how do I write this? I'll write this as 2 would cancel with 2, so this would become mv squared by L. And we have a minus sign, but because we can say that the force would be exerted in both the directions, on this wall and then on the other wall as well, we can just write this thing as you can say that you can write it as an absolute value of the force, which is which is mv squared divided by L. All right,
Sir,
so that's
impulse, the formula of impulse is changed in momentum by time.
Yes, impulse is also similar to force.
All right.
Okay, so is this thing clear? How did we write down the what is this called? Force.
Yes, sir.
Impulse is similar to this thing force, but it's not exactly force, by the way. So it's not change in momentum by time. Impulse, by the way, there is no impulse is what? Impulse is when you hit something. So for example, a very nice example is you have a blackboard in front of you, and or for instance, maybe you don't like physics, you have a book of physics in front of you and you hit it, and as soon as you hit the book, you'll release your punch, right? You'll hit the book and you'll immediately release the punch away from the book. That's when the impulse is happening. So it's just the force that I'm applying for a very small time delta t. So it's force times the change in time. So actually, in fact, it is similar to momentum, right?
Excuse me,
But
sir.
yeah.
Does this have anything to do with centripetal force, which was mv squared over r?
Oh, you mean this expression?
Yeah.
Okay, so that's a good observation. The formula looks very similar to mv squared by r, right? But I mean, the formula does look similar, but it's still a force, and this force, the nature of this force is it does not really have anything to do with a circle, right? Because we started off with a box, and the box is of a squared or a cube shape, right? So it's not really so the expression does look similar to a centripetal force one, but it is not related to the centripetal force, because we never started off with anything having a circular motion, right? You can think in terms of this thing that we are talking in terms of a molecule which is hitting a wall and it's coming back, right? So it's hitting and coming back to its same position. And that's what happens in a circle. It starts from a point and then it comes back to that same point. So there's this force that keeps this object in the circle, and that's called the centripetal force. So it starts its journey from a point, comes back to a point, and then the same thing is happening over here, kind of. So it's starting its journey, but the motion is linear. It's not circular, right? But yeah, kind of relatable with this point, that it's starting and coming back to its same point. So maybe